Good morning, good afternoon, good evening, depending on where you are. Welcome to RT20. I'm Etienne Lezuc, Product Manager at OPAL-RT, and I'll be responsible for hosting and moderating this panel on digital twin to increase resilience of power grid. I'm glad to welcome Henry Huang, a laboratory fellow at Pacific Northwest National Laboratory in USA, who will be chairing the session. I also welcome our 5 panelists. So we have Dr. Taku Noda, Senior Research Scientist at CREAPI in Japan, then Dr. Dominic Kola, Product Lifecycle Manager at Siemens in Germany. Then we have Christopher Pritchard, Head of Product Management, Omicron, Austria. And we have Dr. Teng Jiang, Senior Research Scientist at TU Ilmenau in Germany. And finally, we have Jean-Nicolas Paquin, Division Manager of Application Expertise and Electrical Simulation at OPAL-RT Technologies in Canada. So the panel lasts for about an hour. So right now in the opening remarks. Then we have 10 minutes of remarks by panelists who will share their company's contribution to this topic. Then we'll have a moderated Q&A for 35 minutes. Will be led by the chair. Then 10 minutes open Q&A by the moderator, who's myself, and in the end, some closing remarks. So at any time, feel free to click on the question and answer button at the bottom of the screen. You can send your question, I'll receive them. And we'll be using these questions in the open Q&A in the end. So that's it. I'll hand over to Henry.
Thank you, Etienne, and also good morning, good afternoon, good evening to everybody. Also want to thank all the panelists and also the audience who joined us today in this special virtual format. I have only this one simple slide and also one simple point to make. No two twins are the same. We have never seen the 2 human twins are the same, so the digital twin and the physical twins are not the same either for 3 reasons. First, it's not possible to make them the same because the digital model is always only a partial representation of the physical system. Second, there's no need to make them the same because we only need to model what we care. And the third is we do not want them to be the same because we want the digital twin to do more, to be capable of trying out different configurations and scenarios, which are usually not possible to do in the physical system, especially for the large scale power systems. So these are now lead to some challenges in then how to build, validate, calibrate, and update the model for the digital twin and how to run analytics in the digital twin to support decisions, and also how to perform large scale studies in the digital twin fast enough for decision making. So those are the challenges I highlighted in the white text on this simple slide. With that said, I will leave them for the panelists to address today. And first, let's welcome the first panelist, Dr. Taku Noda from Central Research Institute of Electrical Power Industry. Please, Dr. Noda.
Hello, I'm Taku Noda from Central Research Institute of Electric Power Industry, CREAPI, in Japan. It is quite a strange feeling attending an international conference from home. It's 11:30 p.m., about midnight here in Japan. So, Etienne, could you show the next slide?
Sure.
Got it.
Yeah, actually, this is the digital twin concept for distribution systems, which we are working here in CREAPI, Central Research Institute of Electric Power Industry. If you look at the figure, left-hand side is the real physical system of the distribution system. Now we have lots of renewable energy generation systems such as photovoltaic power generation systems and electric vehicles, and battery energy storages are coming in a huge number of those generators and storages are coming into the distribution systems. And weather, climate, they also affect the operation of distribution system. Of course, each distribution system is different. So distribution systems are different from place to place. So regional characteristics also have a great impact on the distribution systems. And the economic trends also have a great impact. If you look at the right-hand side of the figure, it shows the digital twin of the physical distribution system. Right-hand side is a digital twin, so virtual thing. Every utility, I mean every distribution system operator or distribution company has its own facility database. So their entire distribution system is already in the database. And we have already created a computer system called GRISM. If you look at the right bottom, it shows GRISM. It stands for Grid Simulation, GRISM. That system extracts the distribution system data from that database automatically. So if you select a substation and which feeder, then the computer, that GRISM system will automatically extract the data of a certain specified distribution system, distribution feeders in your computer program. And we are developing XTAP, which is an EMT, electromagnetic transient simulation program. And on XTAP, we have already developed EMT simulation models of all distribution and customer components of distribution systems. So we can automatically extract the data of a certain distribution feeder which really exists in Japan and automatically create a test case for EMT simulation. So that's what we have done for now. And we are now expanding this digital twin concept to include tests. If you look at the bottom, right bottom corner, you can see some test photographs. And we have a test building where there is a back-to-back converter, BTB converter, 10 kVA, which is connected to physical line sections, physical inductor, capacitor, resistor, representing real 6.6 kV distribution system, and we have high voltage test lab inside the building. So we are going to connect these simulation and the testing. Then what we can do is we can run the EMT simulation on a real-time simulator such as OPAL-RT. Then its output will be sent to the back-to-back converter, and then we can test that device, real device under test. And then we can carry out the test as if it is connected to a real existing distribution system. That's what we are developing right now. Okay, thank you very much. This is the brief presentation of our digital twin concept. Thank you.
Thank you, Dr. Noda. Let's move to the next one. Our time is really tight, so let's try to be brief, and so we can leave time for questions and answers. Next would be Dr. Dominika Kohler from Siemens, Germany. Please.
In this meeting, and on the first slide I really want to show you we're serving two customer groups. On the left-hand side we see basically the T&D utilities, transmission and distribution. On the right-hand side we see what we call the grid edge, all the different players that are evolving around, you know, metering at the grid edge, around e-vehicles, storage, and all that kind of stuff. You have three different things.
Dr. Kohler, I'm sorry for the interruption. It sounds like there's some static in the voice. Can you adjust your speaker a little bit, or there's an internet issue?
So I just turned out my camera. Perhaps then the connection is better.
Okay, it's much better. Yeah.
Okay, great. So I said we have the customer groups, transmission and distribution on the left, and we have the grid edge customers, and we do offer three different things: consulting and services. We do offer software products like our PSS suite for simulation of the grid, like control rooms, like data management, also e-car operation centers, and then we do offer grid automation and protection. So this is really hardware then. So on the next slide, if we go one further, you see basically the core vision that we believe many of our customers have, and also that is driving us as a digital grid business unit at Siemens. And the vision really is providing the electrical digital twin in the end to our customers as a single source of truth for a utilities grid data. So what does that mean? In our customers, we typically see there is operations department, planning department, and so on, GIS, market simulation, and so on. Many different departments, all of them with different databases, different tools that can be used. And our main idea is basically to have one electrical digital twin database in the middle as the single source of truth to help facilitate data exchange and also help application of tools from the one domain in the others. There are three benefits we see out of this. This is what you can see on the left-hand side. Benefit number one is really efficiency in data management, data maintenance. Also, imagine you have to do instead of in all the different departments. Number two, the benefit number two is really enabled applications. Imagine you can apply planning, dynamic simulation tools to the operations world, like for example with our Seeger DSA. Or then number three would be data exchange also with externals. Happy to discuss this further.
Thank you, Dr. Kohler. We lost at the end. Are you still on? I lost the slides. And you are muted at the end.
Sorry, I'm back. I shortly lost the connection. I'll share the presentation again.
Okay. With that, let's welcome Christopher Pritchard from Omicron, Austria.
Thank you. Well, I guess I start. My slide doesn't have a lot of content. So as already said, my name is Christopher Pritchard. I'm head of product management. Generally, as Omicron, we're more concerned usually with the physical world and testing relays and other units. But our general motivation always has been to empower people, customers, to provide a reliable power system. So we're currently very carefully following the trend of digital twins and are in active discussions with many manufacturers to make this technology actually available and also usable for customers in the end. And I believe this is really a very important thing, as I think with a power system transformation, there's so much complexity coming in the system that we will struggle keeping to get hold of the complexity we're facing with with power electronics. So digital twins will definitely be a key technology we will need just to be able to drive the power system transformation. So with that, much more, there's not much more I can say, but I'm looking forward to the discussion. Thank you.
Thank you, Chris. Next, let's welcome Dr. Tan Jian from TU Elmano.
Thank you. Thank you for having me today. I'm really excited to be here. Digital twins are one of my favorite topics. I want to give a few words where I come from. Originally, I come from China and live and work at this beautiful university, Ilmenau in Thuringia, Germany. Technical University of Germany, University of Ilmenau is a public research university. We have more than 200 years of history, which we are proud of. It has 5 academic faculty with about 8,000 students and 2,000 researchers and professors. Our department called Power System Department, led by Professor Wesselmann. We have almost 30 researchers and several assistants. We have diverse teams which work on various research projects and industry projects which focus on topics like power grid stability, operation of HVDC grid, operation of converter dominant grid, and interaction DSO and TSO, and so on. Next slide, please. Well, I want to make long story short, digital twins is really the buzzword in recent years. We do have several research projects and applications related to this definition. One of this is like we suggest to show in this slide, we suggest DSO switch from measurement driving decision-making strategy, which they are doing today, to a digital twins assistant decision-making strategy. Means in the future, primary task of measurement is not to support directly the decision-making process, but to establish and improve the digital twins which reflect the physical reality, and to show the operator of our power system what has happened and what is happening and what will happen in the power system. Well, I'm really looking forward to have a nice discussion with you guys, and that's from my side.
Thank you, Dr. Jiang, and also thank you to all the panelists so far, being brief and kept us on schedule. So now, last but not least, from our host company, OPAL-RT, Jean-Nicolas Paquin.
Yes, thank you. Yeah, so you all know OPAL-RT, so I will not spend too much time explaining what we do, but I wanted to have a slide here that explains at a top level what is our vision of a digital twin. In the recent months or recent years, I've had this discussion with many people internally at OPAL and externally as well, and people are asking, why are they talking about digital twins? It's just another buzzword that says simulation. It's a simulation, or it's a real-time simulation of something. Well, I think it's important to define that it is not just a simulation. It is more than that. I think we need to insist on the key attributes of a digital twin. And to me, it's important to say that the digital twin has a bridge of connectivity with the real world, meaning that with data it receives from the physical twin, it can report to other functionalities within the control room or some other applications. You can log some information. You can add some information on top of what you know from the physical twin. You can use it also for control, but it needs to have a bridge of connectivity with the real world. Then another important aspect, I think, of the digital twin is that it's self-adaptativity. You need to consider that the digital twin, if it's a twin, it is a copy or a real-time copy of the physical twin of the real-world system. So in that sense, it needs to have, if it's a dynamic model, for instance, it needs to have parameter identification, system identification, whatsoever. So there are many services attached to self-adaptativity that are possible. It can act as a dynamic observer. Since you have a limited amount of sensoring inside the power system, you're definitely going to use a digital twin as an observer. Something like a dynamic observer, maybe not like a state estimator, but really something that will give you more information, additional information to what exists already. Then digital twin will be a decision and control supporting tool, as my colleagues before have explained. Because of all its functionalities, it will allow to help improve decision making. And it can be used also as a predictive tool. It can respond to stimuli which are coming from the physical twin, but it could also respond to a synthetic stimuli, which is, right now, this is probably the definition we have of a real-time simulator or a simulator. We make it respond to a synthetic stimuli. It's connected with some piece of equipment and you're testing it. So you could use these different stimuli from the real world or simulations to use it as a predictive tool, as a design tool, and a planning tool. And if we can go to the next slide. I think also for those of you who have attended the introduction presentation from Mr. Bélanger, I think it will be important to consider that the digital twin can be used with smart simulation runs, like tools that will allow you to define what are the simulation tests that you should run to actually verify if your control works well, if your system works well, because otherwise there are thousands and thousands of tests that you may run, and you may never find the corner cases that may make your system to blackout. So I think these are important aspects and important attributes of the digital twin. And I will be really happy to know what my colleague panelists have to say about this.
Excellent. Thank you, Jean-Nicolas. With that, we are done with all the remarks from the panelists. We're going to move on to the next section, which is a moderated Q&A. We prepared a few questions for the panelists to discuss. Now, to save time, I will not repeat the question. I will display them on the screen. And also, I would like to ask the panelists to be brief when they address the questions. Now, let me see. I cannot advance the slide at the end. Okay, good. Thank you. So this is the first question. Let's talk about the key drivers. Let me call on the panelists to offer their views. First one, I would like to ask Dr. Noda, please.
Okay, I'm going to answer to this question in view of distribution systems. Traditionally, distribution systems were facilities to distribute electrical energy to customers. But now, exchanging electrical energy among customers is a new important role, as you know, because PVs and EVs are coming into the system. So now the operation of distribution systems is quite complicated and will be even more complicated in the future. So we need simulations for this. Especially, we have to solve the problems of interference among distribution and customer devices. So coordination of the devices is becoming more and more important. For instance, we experienced interference of a large-scale PV generation system with a step voltage regulator, which is a voltage regulator in the distribution system, and interference of the islanding detection relays of photovoltaic generation systems with the distribution systems, and so on. So if we can create a digital twin of distribution system, we can solve these problems. Okay, I'm done. Thank you.
Very good. Thank you, Dr. Noda, and also thank you for being brief. Next one would be Dr. Kola.
Yeah, thank you. That's a great question, actually, and I think Dr. Noda always already made some very good remarks. So let's to add on this. Let's remind us of the priorities of the grid operators that we are aware of. So I think typically they want to talk about resiliency, efficiency, and compliance, right? And the challenges that they really see out there in the market to meet those priorities is, in our Siemens point of view, what we hear, it's actually two things: the complexity that Dr. Noda also already mentioned, and it's also the uncertainty. From the examples we heard, storage, bidirectional power flow, sector coupling, cost pressure, all these kind of things. On the other hand, besides those challenges, we believe that they also have great enablers now in place for the digital twin. So these are also drivers. There is a lot of new digitalization technology going on. For example, graph databases to store huge amounts of data, AI, cloud hosting. So these are all then like positive drivers. And in the end, if we can bring this together, and we can help our grid operators meet those challenges with the enablers, with this overall software assistance systems, I would almost say this would be the digital twin in our point of view.
Excellent. Thank you. Next, let me invite Dr. Jiang to give a remark.
Thank you. This is a very nice question. I totally agree with the point of Dr. Noda. I think digital twins is a change and revolution driven by increasing complexity of our system. We have increasing number of converter-based technology like solar generator, wind turbine, electric vehicle. Means you need to make more prediction. At the same time, the power grid suffer drop of system inertia, which means the oscillation or interference could act more violent than before. Would affect a more grid layer vertically and affect a far distance horizontally. By the investigation or focus or research simulation, you need to include more layer, more facility, more neighboring grid. You can do that even in real time, and you need to do it a higher sampling rate. That's not a state of art could offer. The need of reflection of the complexity of the system, the operation of future system is a digital twins. That, in my opinion, one of the key drivers to introduce digital twins technology in power system operations.
Excellent. Chris, can you add a few as well?
Sure. Am I muted? Yeah. So my short answer would be the key driver, usually drivers is when the customer really has a deep problem. And I think, or utilities have deep problems, and the problem will arise from the integration of power electronics. So I think that will be the main driver towards digital twins. And so if we're not able to heavily standardize inverter topologies and standardize on control algorithms, and manufacturers are still wanting to maintain their intellectual property, so keeping everything closed source, we will need digital twins to safely operate the power system for the future. Also, and you can see here, I have a little bit different understanding of digital twin maybe than what John Nicola described. I would still also see a digital twin as a virtualization maybe of a kind of firmware. And so after that, I think other things will then follow, like twins of protection systems, supervision of distributed energy resources. Those are all interesting use cases that will follow this driver. From a technology point of view, what would be a driver or more a kind of enabler, I think, is if we can achieve to have a kind of standardized manufacturer independent, that's the important part here, twin interface, so tool infrastructure can actually start using these twins in a neutral way, because many utilities have just multi-vendor systems by design, and so that will be a key. And last but not least, I think also what a missing key enabler, a question we will have to answer, is with these systems that are then have a super high fidelity in terms of the simulation, how do we deal with legacy systems where there's no existing twin, where there's the firmware to virtualize is not there, right? Which cannot be considered by the manufacturer in the development. So how do we deal with legacy systems for these simulations? That will also be a very interesting question to me.
Thank you, Chris. Excellent points. I agree with all the points being mentioned. I also want to highlight one thing being mentioned. I think maybe worth further conversation later on if you have time or maybe offline, which is definition of digital twin and or maybe attributes of digital twin. That looks like need more conversation among the community. But for now, let's move on to the next question, which is talk about challenges for the operator and the planners using digital twin. With that, let me this time start with maybe Dr. Jiang. You want to say a few words?
Yeah, sure. Thank you. Theoretically, this question is about how this dynamic model could properly validate it. Okay. Theoretically, there are two types of approach to modeling a process. There are analytical modeling and data-driven modeling. There's two kinds. Analytical modeling approach is based on understanding the physical process to generalize the model in form of mathematical expression in form like a differential equation or differential equation system. Challenge is that with increasing system complexity, like I addressed before. Nowadays, you need to include more layer, more facility, and more active element into the simulation. And the dimension of your differential equation system are getting bigger and bigger and larger. In time, you will have a problem with your simulation, at least numerical problem. One alternative is to switch this to analytical model to data-driven model, which based on observation of the input-output of the system. There are very powerful tools like neural network are really good at approximating arbitrary input-output function. Precondition is you need to have access to this huge data set, and you need to able to process this. Once you have that, it could deliver very good approximation of system dynamic, a very valid model.
Excellent, thank you. Who want to go next? Dr. Noda, you want to go next? Or anyone?
No. This is not my question. Sorry.
Well, if you like, I can jump in, Henry.
Yeah, for you? Please, Chris.
So maybe before I start answering, it would be important to clarify a few terms. We already found out that Jean-Nicolas has also different ideas of what digital twins are, and there are different definitions of this. And usually you can definitely say every model and every simulation always has been a kind of digital twin. I try not to do this and try to keep them separate. So for me, a digital twin in terms of planning operations is more like a virtualization of a firmware or a kind of algorithm. So there I actually believe they are actually not providing any validation really to models. It is actually the twins also need to be validated just the same way. And we saw this from Dr. Noda with his bench testing with real setups. I think it is the key to validation of models is not digital twins, but rather to have a kind of a process in place that ensures the validation throughout planning and operation. And what I'm thinking of is if we're working with digital twins early in planning and then later in operations, it is during a factory acceptance test where I'm validating that my twin is behaving the same way as maybe the physical device under test in a hardware in the loop system. Or I can also validate my twin by using disturbance recordings and validating and comparing them to the twin behavior. So I think it's more validation of models and twins is the same thing, and it should take place throughout the process, and it's not the twin that's solving it really.
So this is Dominic Kohler speaking. I love what you're saying, and I quickly want to also add to this, like especially to the dimension that was also brought in by Henry. What is actually the definition? And Chris, you just added to this, right? So in the beginning, we heard a bit also in the presentation of Jean-Nicolas that the digital twin should be always connected to the physical world. And now we heard the question again, is a digital twin already a digital twin if it's only a simulation? In my point of view, the vision in the end is to connect the physical world with the virtual world, with the simulation. However, for now, I think what we currently can do with the technology that we have today is already a huge challenge to have one digital model of the grid. As I showed in my introductory slide, there are so many departments all having their own digital twins, so to say. So what we believe is actually one of the core aspects is to have one model properly validated and so on that represents the grids that the different departments can use. So there is already for today value in bringing those digital twins, the several digital twins if you want so, together, and then connecting it of course in the long term also to the physical world. So to be more specific then to this question, we believe that model validation is actually at the core of such a digital twin, at a central digital twin, so to say. So when we, for example, sell our tools that we have for this, and we call this network model management, right? So really managing the different network aspects. We always deliver, for example, data validation capabilities. For example, parameter verification, but there are like examples would be power flow calculation engines that are coming along with those modeling databases. We have state estimation as part of this, and we're also working into the future now with rule-based engines. So this can be AI, really using artificial intelligence then to validate the models. But even today, we have consultants who do rule-based checks as a consulting service. I think one thing that I want to mention as a last point for this, for model validation, especially in the dynamics regime, would be research that we're doing in the direction of using dynamic security assessments. So really dynamic simulation and comparing this with phasor measurement units. So wide area phasor measurement units, and then comparing like really then the physical world to the digital simulation, and thus validating how the model looks like.
Excellent. Any more comments on this one?
Full agreement, Dominic.
John, Nicola, you want to add something?
Yeah, I may. I may give. I agree with both of you, Christopher and Dominique. When I defined the attribute as self-adaptive, I was really meaning, you know, if you have a dynamic model within your digital twin, you need to make sure that this dynamic model behaves the same. But I also agree that you can see a digital twin as a firmware copy, a digital firmware copy of, let's say, a protective relay, perhaps a controller. But then again, it could be a copy of your firmware, and still the operator has changed the parameters. How are you validating exactly that? For a protective relay, you'll see it if there's a trip or if there's an event or something like that. For a controller, how do you make sure that the actual controller with its setting is acting as per your model that you're using for planning, per your model that you're using in the operator room? I think this is what I mean by a digital twin should be self-adaptive. It should be used for verifying what is the current state of your actual physical twin.
Good points, excellent points. Is that also let's be sensitive to our time limit. Let's move on to the next question. Which is how to see actually digital twins to assess dynamic security, which actually was mentioned a little bit earlier on this aspect. Now let's see who wants to take a shot on this question.
Maybe I can answer to this question.
Please,
okay?
Noda. Mm-hmm.
Okay. Again, in view of distribution systems, so last year and 2 years ago, we had a very large storms, typhoons, possibly due to climate change. And we experienced large-scale outages in Japan at the distribution level. And in the case of Japan, one customer has 2 routes to substation, distribution substation. It means one customer has 2 distribution lines to distribution substation. So when one route is out, when one route is down, then switches on distribution poles are remotely controlled so that the other route becomes available. This process is automatic and fast, very fast, automatic and very fast. So to create and test new logic of such dispatch system to avoid cascaded failures, I believe digital twins are quite useful for testing and developing new such dispatching system. That's it. Thank you.
Excellent. Thank you, Dr. Noda. Anyone else?
Oh, well, I'll try to answer that.
Yeah, please.
Well, there's a lot of way real-time simulation could contribute, could help. With concern, what we're doing, I would say, in 3-word communication, coordination, and sharing information, which are also keywords of this decade. I did mention before the interaction of DSO, TSO. In fact, they did cooperate a lot in terms of ancillary services to find a new source of flexibility, transfer capability, for example. A lot of this decision-making and action in the operation need a kind of information from your TSO or neighboring DSO. This is change of data by asking, how are you doing? Do you have something for me? Can I get 5 megawatt? Take a lot of iteration process and take a lot of time. In case of a contingency, the operator really need to make their decision quick and action quick. Otherwise, the power system may reach irreversible point which caused by the cascade failure that in worst case could lead to a blackout. By using the digital twins, TSO, DSO could be reflected on the digital twins of the counterparty and update them by offering real-time measurement. So you don't need to phone call your DSO and TSO. You have your DSO and TSO real-time in your control room in that box called the real-time simulator.
Yeah, I totally agree. I think we are in the modern days and still rely on phone calls to run the system. That's kind of the old-fashioned way. Excellent. Okay, let's move on to question number 4. In this question, the keyword is uncertainty, which was already mentioned by several of you. So who wants to take a first cut on this question?
So I'd be happy to jump on this. This is Dominic speaking, and I think one keyword here is uncertainty. The other is planning and operation together, right? So let me start with the planning and operation part first. This is actually one of the core things where we believe there is value of having not 2 digital twins in the planning and one in the operations side, but having one core central network model that then both the planning and the operations department at a company can use. So for example, in the upgrade of the EMS system, you can rely then on the central model. You can exchange data from the planning part into the operations part of the company when a grid gets really then confirmed, when a case gets confirmed and gets transferred to the operations case. And also there's then a lot of increase in efficiency when you want to analyze blackouts. You get switching states from the operation, can then analyze in the long term in the planning department. So I think there's really a key in bringing planning and operations closer together. The other aspect of the question, as you said, is uncertainty. And uncertainty means, for example, via such a network model management, in my point of view, that we can combine different tools and fight this uncertainty to increase the utilization of the power grid. If we are able to decrease uncertainty, increase the and decrease the safety margins, we're able to get a higher utilization of the power grid, and this will be very, very helpful. So, for example, solutions that we're looking at would be especially around all those renewables. So imagine distributed energy resources that a DSO has to integrate into the system. And he gets a request from the end customer. Can I do it? Can't I do it? You know, he gets thousands of those requests, the DSO, and he has to answer it on all this uncertainty. And what he wants to do is basically ask the digital twin, right, to get a quick answer. So I think there's really some value add in this digital twin with a good model and helping to answer those questions of uncertainty around renewables.
Yes, I fully agree. As I mentioned earlier, digital twins can do more than the physical system. Physical system is only one scenario. Digital twins can try many different scenarios, which is especially important for uncertainty, right? Yeah, next. Well, Chris, since you're already speaking, why don't you go next?
So sorry, I was muted. I would just add something, especially to the planning side, because that I think is also very interesting to me. At least, my background is not so much the operation side of things. So the big advantage there, really, of the digital twin is that we can start very early in the process with the quality assurance and the de-risking. of very complex projects. And as earlier we are able to test, the earlier we can fix problems, the cheaper it is. The later we find errors, the more expensive it is usually to fix the errors. So this is really the big advantage of digital twins, is that we can start with our quality assurance very early, before the first brick is laid of the substation we're planning, for example. And I believe with a large amount of inverters, and at least I can speak for Europe, what is planned in the next 10 years in the power system, it is just totally impossible that a physical replica of every instance for a power electronic station is built. So that is completely out of scope, I believe, in terms of the amount of units that are going to be built. So I really believe the future, especially in planning and quality assurance, will be simulation, and more simulation. That's just, yeah, I guess my take here.
Can I make just a brief comment? Is that okay?
Yeah, please.
Oh, okay. I think we should make a clear distinction between transmission digital twin and distribution digital twin, because this transmission digital twin, the transmission system is large, but not as large as a distribution system. So one company can maintain one digital twin simulator, and the company can continuously maintain the system. But in the case of distribution system, because it is too many systems on the earth, so each time we have to download the data from the database, and then we can create one feeder of one digital twin of one feeder. So each time we have to get the data from the database. So the connection to database is the key for distribution digital twin. Thank you.
That's a great point. Thank you all the panelists for offering their thoughts and the views on this aspect. Let me see. One more, go ahead, Chris.
No, that's fine, sorry. No, go ahead. It was just one comment. I think it's not only looking at the one feeder. I think the challenging thing will be in the future is the integration of power electronics, right? It is, how is my power electronic in station A interacting with station B? And it's the interaction that is critical, and therefore I need already 2 HiL systems. So this is just, it's out of scope to do this with real setups.
Right,
so.
Right, good point. Okay, thank you. Now let me see what's the next one coming up. I knew that because nowadays we cannot talk about technology without talk about AI. So this is an AI focused question. So can someone take a shot on this?
Well, I can say about that. Go ahead. First. You can go first.
Okay, thank you. Okay, so if we go back to my suggestion of with the schematic, you've probably seen that digital twin will have multiple instances. It may not just be one dynamic model. It may be different dynamic models. It may be an EMT model with a dynamic model. It can be a machine learning model. Depending on what is the application and what you will do with it. But in every case, I think because the digital twin would be a replica which is validated against the real world, it would be very useful to utilize and do multiple, for instance, multiple simulation runs, not only for predictive simulation, but you can also use it to generate considerable amount of data that you cannot acquire it on the real system. If you wait for the worst event to happen on your actual system, you may wait for 20 years. So if you actually want to have a very robust AI-based control, you will need a lot of data. So I think real-time simulation technology in that sense, combined with the digital twin concept, will be very useful, whether the real-time simulation software is running on the cloud or it's running on a hardware platform. I think it can be used to accelerate the simulations and accelerate drastically the amount of simulation runs that you can get. But again, as explained in the intro, that potential synergy between AI and digital twins is also important to consider for selective automation of the simulation scenarios, because you want to train your algorithms with the corner cases. You want to train your algorithm with the worst cases that may happen, and not necessarily by repeating tests that will give you similar results.
Mm-hmm. Good point. Now, Dr. Jiang, please.
All right, thank you. I want to mention there's a lot of interesting questions there. I was busy answer this question. I would hope other panelists could also. I have seen Dr. Taku already answered some question of that. It's a lot of very interesting questions, but some of questions asking about IT I couldn't answer. It's mighty interesting for you guys. When you got time, you could look for this. So I've got my question. Well, digital twins is a reflection, a mirror of the reality based on which you make your decision. For instance, run your AI-based control. Nowadays, most of the AI algorithms are data-driven. And the key challenge is, of course, you need to be able to process that amount of data set. And if you want to reflect and feedback to a process in real time, in real world, you need to do that in real time. In this case, you need a real-time simulator or real-time simulation. Once you're able to do that, you'd have a portfolio of powerful tools. You could optimize your process based on that. You could tune your controller adaptively, feed forward, feed backward, even change the structure of a controller. That is where real-time simulation, I think a real-time simulator could help a lot and create a synergy. Thank you.
Good point. Actually, I have a dream, which is we can run real-time simulation of many cases and then real-time training of AI method. I think that would be really useful for power grid. Anyway, so hopefully someday we're going to get that. So for now, let me see. We have a couple more questions. I was told that we can have 10 more minutes of time for our session, so I think that's very good. Still, we're still on a tight schedule. Let me see. Let me try this question and see how we go with time, and then we'll see whether we should move on to next Q&A for open questions. So this one is really look at cloud computing, communication, and how they can be useful for cyber physical systems. So, John Nicola, you are ready for this one?
Yeah, I can definitely answer this one. We're talking about digital twin for cyber physical systems here. So, for me, I will take this more like a multidisciplinary digital twin, which means that you may have an expert in power system that will treat the cyber side or the communication side of things or the IT side of things. You may have an expert in power systems that would deal with the digital twin, the part of the digital twin which is about the electrical system, controls, relay communication, and everything. But when you're talking about multidisciplinary engineering, it's really important that there's a collaboration between the specialists. So I think in terms of simulation and the creation of digital twin, frameworks for co-simulation will be very important, like the OPAL-RT orchestra, because then you can have the experts work each on their side on the aspects of the digital twin, and then they can interact together through this co-simulation framework. So I think this will be very important for these multidisciplinary domains for the digital twins. With regards to cloud computing, I think there are multiple advantages to look at cloud computing in the future to integrate real-time simulation technology because of what I said right now. You can have multiple disciplines working at the same time, probably on the same model or different models, but they could work collaboratively through the internet. It can increase in efficiency in the engineering lifecycle. You can get access to a scalable cloud computing power, easy licensing options, and of course, you know, for utilities, one of the important facts is that probably there's a reduced need for IT support and reduced need for personnel that specializes in maintaining the servers and so on.
Excellent. Thank you, John Nicola. Now let me check with Etienne. How do we do on time?
Yeah, I think we're quite short, so maybe we can skip question 7, go to the questions from the audience.
Excellent. Okay. So actually, question seven is very open-ended. It just talk about what's the future and adoption. So I think we can have that's a very broad, open conversation we can have maybe offline. So with that said, I want to thank you again to all the panelists, gave us the remarks and also a lot of insightful views on the questions. Also notice on the Q&A box, as we go through those questions, there's more questions coming about the questions we just been talking about. So I think we could have more opportunity to go back to some of the things we talk about and then have a more conversation. With that said, at the end, I'll transfer this back to you.
All right. Well, thank you, Henry, for joining the session. Thank you to all the panelists for your great contribution, and thank you for the audience for sending questions. So the first one I see here from Vinod, what role can digital twin play in fault detection of real-time systems? So does anyone want to jump at that? What role can digital twin play in fault detection in real-time systems?
Yeah, I can at least try. I think it can play a role when you talk about fault detection systems. And not sure if I answered this correctly, but to my understanding, when you detect faults, it's actually, you can use it as a kind of a monitoring system of, for example, of your protection system. So when you assume you have a fault in your system, your protection system is responding to the fault, clearing the fault, delivering power system data of the recording, the fault recording, fault disturbance recording. At that point, you can then start to analyze and compare the actual behavior of your protection system with the one that has been recorded, with the one that you can compare the actual behavior of the system with the one your digital twin is proposing that how it should behave. Okay, at that point, you have a post-fault quality assurance in your system. At least that is something I can imagine. That's one case. I hope.
Yeah, I would agree with that. Yeah.
Totally agree with that. One of the key problems by pre-detections to detect the things that didn't happen yet. Most of the state of art nowadays is to detect the pattern. This means that the system will give you a sign before something happens. But with digital twins, you have the same system there. You could test the thing real happen in real case. What would be that happen? That show you more information that is pattern.
Thank you. The next question from Mr. Ramachandran, who's saying, so there are quite a many communication standards that are available. So how would the digital twin help adapt to all such standards?
So if we're talking the electricity and the power industry, many transmission system operators, they're often using the SIM, right, the Common Information Model. And what we see, like for example in Europe, N2E bringing together different TSOs, looking for data exchange with the TSOs. Then we have the standard, which is SIM, and we see the same now arising in America. We see it the same in Asia. So I think the SIM standard is one of the core standards for for having one digital twin to describe how power grids work together, also how they can be linked.
This is Henry. I want to extend this question a little bit. I think communication itself may not be a big challenge. There's already, like the question already stated, it's many communication standards, but not just power grid. Anyone else also using the same kind of standards, they can be harmonized. I think that should be fine for power grid as well. But I think there's more maybe challenging question or issue here is in power grid with so many different data formats and data types, and how can we consolidate all the different formats and types so we can have a more comprehensive view and then make decisions based on all the data available, not just based on one kind of data, like only phasor or only scalar, and so on. So how can we combine them? I think that's a real challenge we're facing today. So that's, I would say, a little bit, because we should do more along those lines.
I totally agree with that. I think one key added value of digital twins is you not only run a model for yourself, not build a model for yourself. You build a model for the community. You build a model for other one's usage. So it's really important that you share the same data. At least you define the same communication data type. So other one could reuse that. Otherwise, it's just a normal simulation. It's not only for yourself, but also for like we are power system engineer. We need to have we want to build a system that power electronic could use.
So, yeah. Maybe I can also give an answer. The challenging thing is with integration of different communication standards. I think that was the question, right? How you can ensure that it's working. When you're looking into modern protection automation control systems, we already passed the point that engineering the communications is more complex than the protection system, right? It's a really challenging task to engineer the communication system of, let's say, an IEC 61850 system. And especially at the same time, this is very hard to test, because to test communication, you need the different pairs that are actually communicating. So digital twins can actually support the engineering process on the design process of a communication system by being able to already ensure the correct communication before you're actually going on site installing the system.
Yeah, going back to Henry's point, the importance of data format. So I think everybody thinks about the same common information model, but the common information model is still under development, and as Teng suggested, we should share the data, but not only the data. Of course, we should share the data, but not only the data. We should collaborate for developing, creating SIM-based data format for our digital twin purpose and other purposes. So collaboration would be very important.
Thank you. So our next question from Sarah Vanan. So how do you feel about the enhancement of power system protection systems based on digital twins for protection systems? So do you feel that there will be a shift towards a centralized protection system due to this?
Sorry, Etienne, is it possible to repeat the question?
Yes. How do you feel about?
Can you show that in the text? I have very bad connection.
Yeah, I'll copy it to the chat while I repeat it. So, how do you feel about the enhancement of power system protection system based on digital twin for protection systems? Do you feel that there will be a shift towards a centralized protection system due to this?
Yeah, actually, it's a very difficult question, and I think you know, I think there are two different ways. One way is, as he mentioned, the direction towards centralized protection, and the other way is a very autonomous control and protection system, I think. Mm-hmm. That was my remark.
Yeah. So one remark from my side. This is Dominic speaking. I think this is a very interesting thought, and the enhancement of the power system with regard to protection with the digital twin. So I think one vision that I have in my mind is kind of an how would we call it, an environmentally based protection system, right? So that you kind of have adapted to the environmental conditions, you have simulation running in the background, and you can adjust your protection settings, manage this properly so that the system can be run in a much higher utilization in the end. So this would be my vision, kind of enhanced by a digital twin for the protection system.
In that case, that would be a state-based protection system.
I have another opinion. So I don't think a good idea to run the protection system centralized. So because you always have your communication reliability between that, and you have a latency between that. In terms, for example, of HVDC and fault detection, you need to react really in microseconds. So that is, I don't want to run that in centralized position. So means in the field, the protection system must make the decision quickly. So the second opinion is, while there indeed other concept of digital twins, there are distributed digital twins. Means I will locate part of my modem, my system in the field, in local. So maybe they will have to make the decision. But generally, and centralize the protection system would be dangerous.
Oh,
sorry, go ahead, Chris. No, go ahead.
Chris, just a quick comment, and then we'll have to go to closing statement.
Okay, so centralized can have many meanings, right? Very often centralized protection means a centralized protection relay in one substation. Otherwise, it's a wide area distribution scheme. I think that's two different things we're talking about. And if we're interestingly, this is, of course, the digital twin, when you think it a step further in terms of a virtualized relay algorithm, of course, that could already lead to a centralized computer where you're just running protection algorithms. And so there is some similarity between these two movements. But yeah, I think we should keep this for now separate. Otherwise, again, I think the biggest benefit in the short future is in the engineering of protection relays, where it's about integrating it with power electronics. And there we want to have the digital twin of the power electronic source and see how is the protection behaving on this. I think that is one of the first benefits we will see with digital twins. Okay, thank you.
Thank you, Chris. Henry, do you have anything to add before we close this session?
Okay, if you allow me, just a very quick comment. I think that's one thing is whether we need to have a digital twin for protection. As I think Dr. John mentioned, for the traditional protection, we probably don't need digital twin because it's all local and then need to be very fast. Now, but other point I want to add is for system-wide protection, like remedial action schemes in the Western U.S. power grid or special protection systems, those are system-wide, and then those can benefit from digital twin, and then maybe that's a useful element to make sure that kind of system-wide protection schemes which actually work. So I think that's just my quick thought.
All right. Well, thank you all for your contribution. Thank you for all the attendees for allowing us to extend about 10 minutes. I hope you learned something and you enjoyed this session.